Last talk of this afternoon is by Professor Remigijus Mikulevicius from the University of Southern California, and he's going to talk on the Lagrangian approach to stochastic Navier-Stokes equation and Euler equation.
I would like to thank the organizers for the possibility to be here. And so I'll talk about Lagrangian approach to Navier-Stokes equation and Euler equation as well. So the equation we consider is the following one. So since we move on, I'd like to write it on the blackboard as well. It is an equation in the whole space in RD. So we have partial derivative of the velocity field. It is minus uk derivative ku. Then sigma and mu and epsilon are constants. So constant viscosity constant has a special structure. It's epsilon squared over plus sigma squared divided by 2. Then we have a standard pressure term, and we have a forcing. So forcing has a deterministic component, which is a function gt. Then we have a first order derivative of the form sigma dku white noise kt. Now W is a standard Brownian Wiener process in RD. And we have a stochastic forcing, stochastic component of the forcing of the form fk w dot k. Now
There was some people in the back couldn't read, so perhaps
oh, sorry.
zoom out and then always do it half minute by half.
Okay, thanks. Okay. Thank you. Now, the assumption about WK being a standard Wiener process in RD is not essential. We could take more complicated noise as well. And Lagrangian approach to the deterministic Euler and Navier-Stokes originated in Arnold's paper in '66. So the idea was to think about flow associated to the velocity field as a motion on the as a geodesic on the group of diffeomorphisms. And so this idea analytically was developed in the paper of Eben and Marsden in '70. So they considered Euler and Navier-Stokes as well on the compact manifold without boundary. And in fact, here also was given the first proof regarding the inviscid limit. So if viscosity goes to 0 in the limit, we get Euler equation. Now Cantor generalized the result for the whole space in the situation of the whole space, and this was geometric proof, geometric considerations. Now Eben in '84 gave a concise version of geometric ideas in the paper here, and a translation, a more analytic version of the geometric ideas presented in those papers. So let's say this way was also taken by Konstantin and and TR. So we have derived also a probabilistic representation for the solution of the Navier-Stokes equation. Yes, of the Navier-Stokes equation in the deterministic case here. And but before that, also again very geometric considerations and representations like those were considered for deterministic equations by Belopolskaya and Glicklich. Also, I'd like to mention again geometric paper by Cruzeiro, Flandoli, and Malevian, a recent paper where the Brownian motion is constructed along the geodesics globally in two dimensions. Also, the paper of Cruzeiro and Malevian. So those are rather recent things. So we take the way Abint TR and consider the model, simple model given here. Yes. So first of all, we derive an equivalent equation to the original one. So the idea that rough idea is that it is the same to consider velocity field or a flow associated to that velocity field. So we consider the flow in the following form. So noise here comes from the equation. So equation has W in it, and in order to handle the Navier-Stokes case, we introduce an independent Brownian motion, and parameter epsilon is related to it. So B standard linear process in RD independent of W. So if we look at this equation, so Navier-Stokes is if epsilon is non-zero, and to have Euler if epsilon is 0, right? If epsilon is 0, even with stochastic part, it is an Euler equation. And so if we assume we have a nice flow here, so it produces a flow of diffeomorphism. And take the inverse and introduce the following field Vtx. So u naught x is initial velocity field, and in the definition of G and Fi here we use the data in the equation. So Fit is this matrix times Fit and T. So Fi are components of the random part of the forcing term in the equation, and also F and G functions F and G are deterministic here, and GT has a following structure. Again, if sigma equals 0, so if we have Navier-Stokes, so this term disappears. And so if we now take V tilde t, which is the product written here, so it turns out that ut, so the solution to the equations that we are considering, velocity field can be represented by the following formula. So we need to take script S is solenoidal projection. So what we do, we take solenoidal projection of this product, and then conditional expectation with respect to FTW. So let's I'll give some details. How do we get at it? Yes, so simply, if we take the inverse, it satisfies, if we assume differentiability and so forth, it satisfies the equation written here. So similarly, if we can differentiate, we can write the equation for the conjugate matrix to it to this. And so we can recognize here familiar structures close to the equations that we are considering. And also, if we have an arbitrary random field represented that way, so now we are not specifying what are G and Fi, and apply Ito-Wenzel formula for the composite field. So we put inverse of theta into this velocity field. So for HTX then, sorry, it goes. It takes another page. Yes. So by Ito-Wenzel formula, we obtain the following relation for the differential of H. And now, if we take product V tilde that we considered, so it's transposed of the derivative matrix times HTX. So now we go with Ito formula, right? So we do not need Ito-Wenzel in that case. So if we apply Ito formula, we get this. And so it looks again similarly to our original equation. So the next step is to take solenoidal projection of both sides of this equation. So let's say V tilde is V. So this is solenoidal projection plus gradient term. And then we notice the following. So if we take this expression into the sum of these two terms, right? We get the same expression with solenoidal projection plus gradient term. And basically, it seems we are doing formal tricks, but introduction of A star, F psi tilde, helps to produce the structures, to produce the gradient written here. And after that, so resulting equation looks then so it's almost like our original equation, except we have U and we have V bar here, right? And also we have, let's say, strange terms like this one. But our choice of Fi and Gi was free. So now let's choose a particular form of Fit and Gt. So if we choose Fit and Gt in this particular form, we arrive at this equation. So now if we compare it to our original equation, the difference is only here. But the other thing, important thing, there is no Brownian motion B in this equation. So ut itself is FWT adapted, right? But V bar is not WT adapted. So what we do, we take conditional expectation here with respect to FWT. If we do that, we have for the conditional expectation, we have the same equation, right? But now everything is measurable. And when we take conditional expectation with respect to FWT, this term will disappear, right? And so what we are left, if we consider now the equation for this, it is equation like this. Only U is replaced. U is fixed, but U is replaced by V bar. But with respect to V bar, if U is fixed, it is a linear equation. And so we know uniqueness for this equation, which tells us that U must coincide with this conditional expectation of V bar. So what's the result of these considerations? So it is the following. The result is the following equality. So ut, the solution ut is a conditional expectation of the solenoidal projection of the expression here. So again, what it has in it, so it's u naught is given field, and also g and phi were expressed using the initial data. So it's not the solution to the equation. In fact, it is an equivalent form of the equation. Why? Because inside of it, inside of this equation, it has kappa here. Also, inside of g and phi is a flow eta. So who depends on u? The flows were defined. So the flow eta satisfies the following equation: ut eta t plus epsilon b dot t plus sigma w dot t, right? So eta, so kappa, which is inverse of theta, is a function of u. So you can interpret this as an equation for the velocity field u, which is a different form of the original equation that we are considering. So if we denote now the right-hand side by kt etc., so it is what we have on the right-hand side is a functional of eta. So since g and phi are defined using integrals, so in fact it is a functional of eta s of the flow up to from 0 to time moment t. In particular, if the equation is Euler, so if epsilon is 0 and we do not have Navier-Stokes, so then conditional expectation, so then b part disappears, and so there is no need to take conditional expectation, and we have the following equation in the case of the Euler, right? Also, if equation is deterministic, so sigma is 0, there is no w at all, then the conditional expectation becomes a simple expectation, right? And so it is equation for the velocity field, one can say representation of the solution for the deterministic Navier-Stokes equation. As I mentioned, one way is to look at it, for example, or at the equation right here, as an equation for u. But an equivalent thing is to consider an equation for the flow associated to eta. So how do you solve the equation? So simply, k now is a rather specific, almost explicit functional, right? So the idea would be to solve this equation for eta t, right? And then velocity field is so simply plug a solution to this equation into the functional, and so this is the velocity field that we are looking for, right? And so technically, even if we look at the equations that we have, it is we could consider, instead of this, we could consider an equation for phi t, which is a difference right here. So if we do that, so all noises go inside, and in fact then we have an ordinary differential equation, right? And also this suggests the following. So when we really want to apply this equivalent form of the equation, we need, let's say, to think about function spaces, about the way go back and show really the equivalence of these things. So if we look at phi t, which is here, so you can interpret phi t as a deviation from the diffeomorphism. So identity I is simply identity map, so it's Ix equals x, right? As a deviation, since this is deviation, we could go with Sobolev type spaces. Diffeomorphism, since we have the whole space here, is not Sobolev class, right? So Ix equals x is a simple diffeomorphism, so it's not integrable and so forth. But for a small deviation from the initial diffeomorphism, from the identity, we can use Sobolev spaces. So as function spaces, we go with spaces with weights. So Wx here is a standard weight that is used in the whole space. So it's 1 square root of 1 plus x squared. So it's basically 1 plus x, right? And so in fact, our choice of delta is so that we'll consider functions decaying at infinity. So perturbations are really small. Yes. So what we now we simply describe the so we need solenoidal projection in our formula, in our new form of the equation. And so solenoidal projection can be given explicitly in this case. So simply go with Newton potential and define operators the following way. So C0 infinity is dense in all these weighted spaces. And
can I ask you a naive question before you?
Yes.
Not to slow you down.
Yes.
So if you look at the Lagrangian particle representation, right?
Yes.
There's not much difference between B and W. You could have summed the two, right? What's B? And those are two independent Brownian motion.
Right. Yes.
So you could have actually.
But the equation has only W in it.
Yeah. So that's not sort of symmetrical, right?
No. So we simply we introduce B to produce epsilon squared here.
Yeah.
Yes.
And the sigma equal to 0 case is the Charles Peskin derived in the 70s, 80s, or 90s.
Probably,
right.
Yes. Probably.
You get the deterministic equation.
Yeah.
But it doesn't come symmetrically, so I know I follow the derivations. Okay.
Okay. Yeah. So we define operator Ti, which is a very specific operator given here. And so it is a smoothing operator in the spaces with weights. So if we choose parameter theta, and so P satisfying this, and L which is non-negative, so it maps HL to HL plus 1. And so we can describe gradient and solenoidal projection using this operator T. So again, it is so solenoidal projection turns out to be what's written here. And so it is good to have this smoothing property of Ti if we want really to apply this form of the equation. Yes, and so G definitely then is maps HL plus 1 into HL plus 1, the same with solenoidal projection, right? And these are continuous. And so we use it for the to get local solutions. You can use it to get local solutions of a Euler equation. So the following theorem holds. So if theta is in 1, 2, p is greater than 2, theta satisfies this equality. So consider the case when epsilon is 0. So there is no Navier-Stokes, no Navier-Stokes part in this equation. And if we assume that initial data belongs to HL plus 1 and F, so F is a stochastic forcing term. So if F is in HL plus 2, so we need one derivative more. So then there is a unique maximal, so local solution U of the class HL plus 1 P, P theta plus L. Now we need HL plus 2, so one derivative more, if only if sigma is non-zero. If sigma is 0, then F would be of the same HL plus 1 as well. So sigma is a number at the first derivative. So if sigma is 0, we still have a stochastic forcing. So but if sigma is 0, then it would be HL plus 1. So since we are at Euler, so Euler with random forcing was considered by Kim very recently, but not this method was used. So he started with deterministic case, and so he added stochastic forcing, and his spaces are different. So it's in H2 alpha, this space in this. So how do we now solve this equation? So simply we look at the formula, the structure of the representations that we have, and so introduce. So this is a matrix corresponding to G, so to deterministic parts. So G is a deterministic component of our forcing. F is a stochastic component of the forcing. And yes, and so representation involves two integrals, H1 and H2. So one of them is stochastic, and so the basic part inside of the formula is a sum of two integrals and of the gradient of the initial velocity field. And L is at least 2 here, so solution is in L plus 1, so we have classical solution here, local classical solution. Yeah, so then the functional that we need to consider in Euler case has the following form. So simply we need Ti applied to what's written here. So it is a solenoidal projection of what we have. And so technically it is convenient to handle this H inside as a additional variable. And so let's consider what's written here as a function of Tx theta and Th, which is written here. And so we approximate. So how do we approximate? So if we replace this H by Y, so first we truncate. So Fn is smooth function with compact support. It is 1 between 0 and 10, and 0 if the variable is greater than n plus 1. So it is smooth truncation of phi and y. So the solution is the solution we obtain is bounded in HL plus 1, but so we truncate not by one order lower, but we truncate with HL. And then we mollify in X, so we take convolution of the whole thing with standard modifier double W nu, and so H was taken out. So we consider an equation for phi t and y. So the solution will depend then on so truncation parameter, modification parameter mu. And so this is first component. So as we can see, it is an ODE, only it is ODE in Banach space in HL space. And the second is equation for y. So it has stochastic integral in it, which is truncated as inside as well. So y at 0, so it's a mistake. It should be gradient of u naught here, and phi at 0 equals 0. And so what we do, we solve first equation for fixed mu. So since this is most, we have a solution depending on n and mu, and then so the question is to obtain for fixed n. So for the case with truncation, we obtain the estimates independent of mu of mollifying parameter, and so here. If we look at the formula, the representation, so it has inverse of the diffeomorphism in it. So for the diffeomorphism that we have to handle, all of them has the following norm finite. So this is simply supremum, so it has a linear growth, right? So standard case is eta x equals x here. And first derivative has bounded. But then, starting with the second derivative, it is in HL, certain HL space. And so first of all, if we think about diffeomorphism satisfying this inequality, so this is important that infimum of determinant would be strictly greater than C1. In fact, if eta belongs to this space and has this property, it is diffeomorphism then. And so there are constants depending on k and C1, so that if we take the inverse, right, the following, so the norm of the inverse is bounded by this constant depending only on k and C1, and also when W is a weight in the definition of Sobolev norms. So the weight, if we replace x by diffeomorphism, it can be bounded from below and from above. So Wx can be replaced in that regard by Wn in all the estimates we need. And also, so this is, if we take diffeomorphism like from LKC1, right? So we have, for example, the following estimates for the derivatives of the inverse, right? So it can be estimated by similar expression for eta for the original diffeomorphism, but definitely constant has depends on C and from k and C1, right? So it's something highly nonlinear that belongs to eta. And also, let's say, if we look at the highest term here, so you see so W is a suitable weighted norm. So expressions are very long, so I didn't write specific thing here. But second derivative is estimated by the second derivative. Third derivative is estimated by the basically third derivative of this plus possibly power of lower derivatives of eta. The same is if L is greater. So even clearly if L is greater than 4, so dl is estimated linearly by dl and then possibly a power of the estimates below. So we get estimates step by step, starting with the function, first derivative, second derivative, and so forth. Like we do with ordinary differential SDEs, when we went to estimate derivatives, shows that the flow has bounded all derivatives. So we start with the first derivative, second, and so forth. And so similar Similar picture is here. And also for for sufficiently small v's, so perturbation of diffeomorphism, right? We denote k inverse of eta and k bar inverse of eta plus v. We have that the difference is also definitely in HLP delta, and also can estimate the differences. Now, what is important here? So first derivative is estimated. So the bound involves second derivative eta. So and here is v 1p delta norm. So v is increment here. And so similarly with higher order derivatives. So L minus difference of L minus 1 derivative again is estimated by L minus 1 derivative v, but again the bound involves one derivative higher. So truncation helps here, and so what we get is uniform bounds. So step by step we get uniform bounds for independent of epsilon for L plus 1 derivative, and to have basically Lipschitz continuity for the lower orders up to L. But again, we cannot, let's say, directly go to the strong convergence approximation. So we need to combine weak convergence and pathwise uniqueness. So estimates like this give pathwise uniqueness of the limit. But in order to pass to the limit, we need to use weak convergence. But weak convergence combines with the pathwise uniqueness gives strong convergence. But it is convergence in L with appropriate weight. Also, so there's so formula, and also the other thing, if we take now also in the representation formula that we have, we see H is in HLP delta, and we need to consider H of eta. So for the combinations like this, we have the estimates written here. So for example, if we constructed the flow, so here is we apply the formula, so we will get that flow U belongs to the space is bounded in HL plus 1 and strongly continuous in HL. So formulas are long. There are many technical things here. And so despite simple structure of the equation that we are considering, so the problem is not easy. But on the other hand, the estimates that we have, in fact, one can see that they are independent of really whether epsilon, for example, is strictly positive or not. So what if we want to move from the Euler to the Navier-Stokes case, which means epsilon is non-zero, right? So the situation is much more complicated. For example, think about truncations. So here everything is FWT measurable, right? So truncations, that's fine. So tau is first moment when our solutions exit something gives local solution, but it's not so if we have epsilon and if we have beta t. We cannot stop beta t. It can be stopped. We need a local solution. So moment random time interval must be FWT adapted. So BT can be stopped. So more sophisticated truncations are needed if we want to apply this method. I'm trying to do that. So thanks for your attention.
So the, yeah,
Yes.
maybe
Yes.
possibly.
Thank you, there are immediate
Yeah,
questions.
so the point is
Yes.
you are trying to get higher order suburb. So let's start with the deterministic Euler equation. Deterministic Euler, let's say 3D.
Yes.
So you have a L2 estimate, but there's no H1 estimate. So what you do is you have to go to HS, this Kato technique of HS S bigger than n by 2 plus 1 at the first shot. Now, if you try to put a noise term, since in the process of getting these Kato estimates, you have to use this Moser type inequality or Kato-Ponsa type inequality, and you take an expectation. Maybe that doesn't work, or maybe you have to do work on. Is that why you need to go to Lagrangian methods to estimate?
Oh, so first of all,
Why don't you do?
Yes.
If you try to take directly.
yes. So what I really want to do
Yeah.
would like to do is to obtain implicit limits as epsilon goes to 0. So
higher order suburb
to get Euler from Navier-Stokes, right? And so because the representation itself, it does not depend on, let's say, that you have non-degenerated epsilon or so. So you have representation, and the estimate does not depend on if you have an epsilon. They do not depend on epsilon. What size of epsilon you have here. So it would be a way to show that the limit of Navier-Stokes, stochastic Navier-Stokes, is a stochastic Euler. Well, a simple fortance, and so the model is very simple here.
There's a probabilistic representation of a constant in an year. Am I right in thinking that you cannot extend their approach to a stochastic version because they have
Of whom, sorry?
Constantine and year?
Yeah, so so it's probabilistic representation of deterministic, right?
Yeah. And you
Yes.
cannot extend that approach to the stochastic version because they use a McKean-Vlasov representation. Am I right in saying?
No, so this is an extension of the representation.
Right.
So it is an extension. So the representation itself is so if you remove noises, right? So you have a representation of a year. Yes.
So, in your work on Euler equations, you work in the whole space and you paid a lot of attention to the weight and the estimates. What about a case if it was really a compact manifold instead of the full space?
So my preference to the whole space because everything is explicit, and it's very abstract for me, manifolds or so.
Some bounded domain or torus, if you take torus.
Yeah. So again, it's I prefer the whole space because of explicit things. So everything is explicit here. You can really see what are operators, how do they look like, or so.
So you don't know what would be happening.
No, I don't.
The estimates you obtain is for finite time. Time depends on the initial condition.
Right. Yes. So for finite time, of course, yes, it's local solution only. So the other thing would be, let's say, probably to obtain this way global solutions in 2D. So I don't know this yet. Yes.
I didn't quite get what was the structure in space of the noise.
Sorry, what?
The structure in space of the
Spatial structure of the noise.
Oh, so it has very simple, no spatial structure at all.
noise. I see.
Yeah, so it's very simple. Yeah, yes.
Infinite number of Brownian motions.
Yeah, so W could be infinite number, but here B's is in order to produce viscosity epsilon squared, so you do not need much structure. simple B produces this epsilon squared.
Yeah, but the question has to do with the fact. I mean, I didn't quite see how you got it. I mean, at one point you were introducing the constraint. The eta, of course, is not by itself is not yet solenoidal. So the eta had to satisfy the requirement
Right,
of the
yes,
gradient.
yes.
Yes, and how does this somehow? Does this mean that you have to impose something on the W space in general?
So it cannot be white noise in space. No, not at all. But as I mentioned, so let's say here's a forcing term like this. So I took standard Wiener, but instead of standard Wiener, it could be Hilbert space, and so Fk Hilbert space valued. So this is dot product in Hilbert space.
Yes,
That gives RD vector.
And what would be the condition that ensures that you are really that the determinant of eta stays bounded from below, of gradient eta?
Sorry, what?
The Jacobian. That the Jacobian stays bounded below?
Jacobian stays. When we take solenoidal projections, we get.
But you were starting, you had the condition already on the eta, right?
I understood. Yes, so simply small time. It's a small time interval. So it's a perturbation of diffeomorphism. Initial one is Ix equals x. So we start from the initial and small motion, small motion of that. Yes.
Questions? Then thank you again.